This video a little differently. I think you'll like this better because I'm going to give you the notes and or you should have these provided for you and just talk through the problems that I already have worked out. I think that will make it go faster and you'll still be able to follow along. So this was a homework problem and I want to do the solution, give you the solution for that, and then I'm going to extend the problem just a bit. So this is about the teenage drivers. An insurance company checks police records on 582 accidents selected at random and notes that teenagers were at the wheel in 91 of them. Create a 95% confidence interval for the percentage of all auto accidents that involve teenage drivers. So we know that N equals 582, and we can get P hat by taking 91 divided by 582, which gives us about 0.1564. Before we can do a confidence interval, we have to check conditions. So we are told that the sample is random. Make sure that you don't just say random. When you list your conditions, you need to actually be able to tell that you've read the problem and don't just provide like a list of what those are. The second thing I said here, since it's random, each person should be independent of others. Then we need to check to make sure our success failure is both greater than 10. So n times p hat is 91, which is greater than 10. And n times 1 minus p hat is 491, which is greater than 10. And we also need to check that it's not too large. So 582 is definitely less than 10% of all accidents. So our conditions are met, which means that we can create a 1 proportion z interval. Like I've said before, get in the habit of naming your interval. It's very important. So here is our recipe for the confidence interval. We take our statistic plus or minus our critical value times the standard error of the statistic. Keep in mind that is on your yellow sheet, so if you're not sure where that is, you might want to double check that. Then we know our critical value for a 95% confidence interval, the z-star, is 1.96. And again, I've shown you where you can find that on your yellow sheet. So using that, our statistic is p hat plus or minus our z-star value. This is our standard error of our statistic. You plug everything in. What you see right here is a screenshot of my calculator screen. I went to stat and then test and chose the 1 proportion z interval, and then that is the interval. Okay, and it's fine to use your calculator to do that as long as you have named the test or named the procedure that you are going to use, the 1 proportion z interval, or if you provide the formula, then you can use your calculator to make that computation. So here's our confidence interval. Part B says explain what your interval means, and you always do that in context. So it means I am 95% confident that the true proportion of accidents involving teenage drivers is between 0.1269 and 0.1859. One of the things you want to make sure in your interpretation, make sure that there is nothing that you say that implies you think that you're talking about just the sample. So you don't want to talk about the sample that you took. You are talking about all accidents involving teenage drivers, not just the 582 accidents. We're not talking about this sample. We're talking about the population. And you want to make sure that you are clear on that and that you don't give any reason for someone to believe you're talking about the sample. Part C says explain what 95% confidence means. 95% confidence means that in repeated samples of size 582, 95% of the confidence intervals created will capture the true proportion of accidents involving teenage drivers. It is very important that you have an S on the end of your intervals and not just talking about one interval. Make sure that you recognize that every time you draw a new sample, you will get a new p hat value and a new confidence interval. And it's 95% of those confidence intervals will capture the true proportion and then have your context in there. In Part D, a politician urging tighter restrictions on drivers' licenses issued to teens says in 1 of every 5 auto accidents, a teenager is behind the wheel. Does your confidence interval support or contradict this statement? Well, since 1/5 is 20% or 0.2, that's outside our interval. So our data, if you look at our interval, it's completely beneath the 0.2. So our data suggests that the true proportion is lower than what the politician states. So that gives you an idea of how you should have done that homework problem. And what I want to extend this to now is remember that our formula for, let me add something to this. So our formula for our confidence interval was the statistic plus or minus the critical value times the standard error of the statistic. This part right here, the critical value, which is our z star for this one, times the standard error, that's called the margin of error. So we have our statistic plus or minus our margin of error. So remember in the problem we just did, p hat was 0.1564. This was our confidence interval. So what is the margin of error? Well, the margin of error you can find by just taking one of the endpoints. So I took the upper endpoint and subtracted p hat and got 0.0295. Keep in mind that the p hat is right in the center of our confidence interval. We built this confidence interval around p hat. So p hat is in the center of the interval, and that's always true for every confidence interval you do for one proportion z intervals. So then our margin of error is just the distance between p hat and one of the endpoints. I could also take 0.1564 and subtract 0.1269. That's the margin of error. So ideally, we would like the margin of error to be as small as possible. So sometimes we want to think about, well, what if I want a margin of error? In this case, I want to reduce it, and I want it to be less than or equal to 0.02. But I don't want to reduce the confidence level. So I want to maintain my confidence, but I want to reduce my margin of error. So remember, this is the portion that's the margin of error. So the critical value, z star, times the standard error of the statistic. In this case, the z star is 1.96. So the first thing I did, if I want my margin of error to be less than 0.02, I divided both sides by 1.96, and this is what I got. So how do I determine the necessary sample size if I don't know p hat? So now I want this, I'm trying to reduce my standard error to this amount. I don't really know p hat and I don't know n, so that puts me in a predicament. So you have two options. One of them is to use a value of p hat from a previous study. So sometimes they'll report something that was a previous study and you can use that p hat value. So for example, I'm going to use the p hat value that we had from this example here, from this study. So p hat was 0.1564. So I'm using that, and here's 1 minus p hat divided by n. I'm taking the square root of that, so I'm just plugging this in. And I need to solve this inequality. Now, I went through all the steps for you. I'm only doing this once. This is algebra. So what did I do? I squared both sides, and you can see that. Then I multiplied both sides by n, because I didn't want the n to be in the denominator, so I multiplied both sides by n. Then I wanted to get the n by itself, so I divided both sides by 0.0102 quantity squared. I just switched it over, so n is greater than or equal to this. And then I grabbed my calculator and worked it out. So I get n is greater than or equal to 1,268.16. Notice that n has to be greater than that, so I have to round up. I have to go up. You don't round, you have to go up to 1,269. So in order to have a margin of error of 0.02 or less, I would have to take a sample size of 1,269 instead of what it previously had been. That's one option. But sometimes you don't even know a p hat value from a previous study. You might not have that. So what do you do then? Well, in that case, you use p hat equal to 0.5 as a conservative estimate, because this is going to give you the largest sample size which is why it's a conservative estimate. So if you plug that in for p hat and 1 minus p hat divided by n, and I did not go through the math on this one, you can verify that, you get n is greater than or equal to 2,402.9, which means n would have to be 2,403. Now look how much bigger that is than the previous one I did, 1,269. And that's because look at the p hat value. So this was a lower p hat value. And when I used the larger p-hat value, like the 0.5, it's a more conservative estimate. It's going to give me the largest possible standard error that I could have, which ideally, if I could avoid that, I'd rather avoid that. But if I really, truly don't know what to use for p-hat, then this would be honestly what I would need to use. So that's what you do if you have to have a certain margin of error. You have to calculate the sample size that you would need in order to get that. The next problem I want to go through is problem 22 in your textbook. And it says in 1998, we kind of have an old textbook, a San Diego reproductive clinic reported 49 live births to 207 women under the age of 40 who had previously been unable to conceive. Find a 90% confidence interval for the success rate at this clinic. So we've got N is equal to 207, p-hat is 49 out of 207, and of course, got to check our conditions before we can build a confidence interval. So my conditions, I'm not told that it's random. However, it seems reasonable to assume the 207 women are representative of all women with that health condition. Now, it wouldn't be right to say representative of all women because these are women who had previously been unable to conceive. So you need to make sure that you specify something like that. The next thing I said was each woman should be independent of the others. There's no reason to believe that that would be untrue. Then I check my success and failure condition. N times p-hat is 49, which is greater than or equal to 10. N times 1 minus p-hat is 158, which is greater than or equal to 10. And 207 is less than 10% of all such women who had previously been unable to conceive. Because the conditions are met, I'm going to do a 1 proportion Z interval. Name the procedure that you're going to do. You've heard me say that lots of times. Then I plugged the values into the formula. I didn't write the formula down. I just used the numbers plugged into the formula. I didn't actually calculate this by hand. I went to my calculator and wrote down the confidence interval. And you can do that. That's fine. So we get our confidence interval, and now we have to interpret it. So here's what we say. And you'll notice they all sound alike after a while, except the context is different. I am 90% confident that the true proportion of live births at this clinic to women under the age of 40 who had previously been unable to conceive is between 0.1881 and 0.2853. So again, be careful that when you read over your interpretation, make sure that you never say anything like, I'm 90% confident that the true proportion of births in this sample, don't ever say anything about the sample, because this is about the population. We are making an inference about the population of the women at this clinic. So not about this particular sample. Part C, explain what 90% confidence means. 90% confidence means in repeated sampling of size 207. 90% of the intervals created will capture the true proportion of the live births at this clinic. Again, the idea that every time you draw a new sample, you get a new p-hat value and you get a new confidence interval. And they're going to be different because of sampling variability. Part D, would it be misleading for the clinic to advertise a 25% success rate? It would not be misleading because 0.25 is in our confidence interval. So it would seem reasonable that they perhaps have a 25% success rate. And the last problem, still dealing with that same reproductive clinic. The clinic wants to cut the stated margin of error in half. How many patients' results must be used? Well, we want to cut the margin of error in half while maintaining 90% confidence. So remember, our margin of error is made up of the critical value times the standard error of our statistic. So since Z star is staying the same, so that's going to stay the same, we need to cut the standard error in half. Notice the denominator. We have a square root of 10 because it's under the square root, so it's also the square root of 10 in the denominator. So if we want to cut this amount in half, then we have to make n 4 times larger because the square root of 4 is 2. So if we make our sample size 4 times bigger, we can cut our standard error in half, which means we'll cut our margin of error in half since we're keeping our confidence level the same. So 4 times 207 is 828. That would be the necessary sample size if we wanted to cut the margin of error in half. So then in part B, they say, do you have any concerns about this sample? And the only thing that might be, depending on the size of the clinic, depending on the population of the potential patients they might have, the 828 could be more than 10% of that population, and then we wouldn't have all of our conditions met. So hopefully that helps give you an idea of the details you need to include in your confidence intervals for proportions and all the information that you're going to need to be successful with these problems.